Welcome to this first introduction to data structures. Today we're going to look at elementary data structures. And we're going to start by looking at abstract data types versus data structures. And as an example, we're going to see, as an example of an abstract data type, we're going to see stacks. And then as a data structure that implements stacks, we're first going to look at fixed size arrays and then growable arrays. And in the overall course, we're in this third part here. So we've seen how to design algorithms, how to analyze algorithms, and now we're going to look at data structures. Okay, so what are abstract data types? Let's first look at an example, and that is searching. So let's say we want to have a data structure for searching in a set of numbers. And we've seen this example before. So here I'm comparing the running time of search for Python lists versus Python sets. And in a Python list, searching takes linear time in the input size. And that's not surprising because that's simply the linear search that we've already seen. And for searching, we also already have seen that it matters how we store the data, because if we store the data sorted in an array, we can do binary search, and then searching only takes order log n time. But as this graph shows, if we store the data in a set, then searching, it seems, actually takes constant time. So both lists and sets allow to search, but if we're primarily interested in searching, then we should be storing our data in a set. And the question is, how can searching be that fast? So sets we're going to look at in a later lecture, but the key here is how we're storing the data. So data structures tell us, or data structures are about how we store the data and how we organize it, and then how to access and modify it. So access using operations, and then modify using operations that insert or delete data into the data structure. And examples are arrays, linked lists we're going to see today, and later in the course we're going to see hash tables, heaps, and dynamic sets. So those are data structures, and an abstract data type, in contrast, simply defines the functionality that we want to have from the data structure. And examples that we're going to see today are stacks and queues, and later in the course we're going to see dictionaries, priority queues, and dynamic sets. So for the data structures, I said dynamic sets. I meant the data structure that we're going to see for dynamic sets is are actually binary search trees. So abstract data types describes the functionality that we want to have from a data structure, and then data structures implement an abstract data type. And when we define a data structure, we always have to think about how are we going to store the data, and then how do we implement the algorithms that provides operations that the abstract data type asks for. So why not directly work with data structures? Why define abstract data types? So abstract data types are independent of the implementation, and that has various advantages. For instance, if we need a data structure for searching, then we don't have to think about the specific data structure that we're using, but we simply can assume we have an efficient data structure that allows us to search, and we can focus on our problem instead of thinking about that specific data structure. It also avoids logical errors when we program using the abstract data type, because then we don't think about the data structure and various methods that has, but in the example of searching, we're simply going to use it to search. It also allows us to change the implementation, so we could have a more efficient method for searching, and then we just use it in the background instead of our old method. Which also means we can have different implementations where the various implementations have different advantages. And then for larger programs, it has simply the advantage that it's easier to kind of manage your program. So much about abstract data types for the moment. What we're going to see today, we're going to see stacks and queues, and as implementations of stacks and queues, growable arrays, or first fixed size arrays, then growable arrays, and finally linked lists. And then in the later lectures of the course, we're going to see as an abstract data type dictionary and hash tables to implement dictionaries, priority queues and heaps implementing priority queues, and dynamic sets and binary search trees to implement those dynamic sets. Okay, so let's start with the abstract data type stack. So here you see a stack, and that looks yummy. Anyway, if I want to take a pancake, I will take the pancake on the top, which is also the last pancake that was put onto the stack, and that's how stacks work. So stacks store elements. So we have a set of elements we can insert and delete, and we do so in a last in, first out scheme, which means, okay, insert for a stack is called push, so we can push an element onto the stack, and then it's on the top of the stack. And then if we delete an element, so when we take out an element, that is called pop, and the element that we're going to pop is the last element that was inserted. And additionally, as operations, we want to have size and is empty. So what are stacks used for? Stacks are used, for instance, if you have a history, then if you want to kind of go back in time, I mean, if you want to go one step back, then you're going to access the last element that kind of was added to the history, or likewise, if you want to have an undo, the last operation that you want to undo is actually the last operation that you did. If you implement recursion, then recursion is also, so if you think of a recursive algorithm, and then you kind of go into kind of a recursive step, and eventually your program wants to go back, and that information you can also store in a stack, although we won't do that directly. And stacks are then also used simply kind of as auxiliary data structures in more complex algorithms. Now, a simple way to implement a stack would simply to put it into an array. So we have an array of a certain size. In this example, it has size 20. And then we can simply add elements. So we start adding an element on position 0, then the next element position 1, 2, and so on. And then if we want to remove elements, I mean, we can store the information of what element we added last, or what index we added an element last, and we're going to pop that one. And in that way, we get a simple stack. Okay, so maybe I should briefly say, so we have here a class called capacitated stack. So if you haven't worked with classes yet, that is not really important to kind of see what's going on. So the reason we have a class here is because we want to we see kind of the stack that we're going to use as an object with properties, and these properties are simply then the parameters of the stack, so of this class. So a stack has a capacity, meaning how many elements can I store on the stack. It has a list of items, or an array. We want to see this as a kind of array of items. It's of course implemented using a Python list. And we also store how many items currently are in the stack. Again, the operations that we want to have are size. So how many elements are currently in the stack? Is the stack empty? Adding an element, so push, and removing an element, pop. So I'd suggest you pause the video and simply try to implement these methods, maybe simply on paper. Okay, so let's have a look at how these methods could be implemented. If I want to know how many elements I'm currently storing, I mean, I stored that information, that's count. So I'm simply going to return the current count. Similarly, if I want to see whether the stack is empty, I can simply check whether count is 0. Now push and pop will be more interesting. So if I want to push, I mean, in principle, what I need to do is, think of initially count is 0. And the first element that I want to push, I want to actually kind of place at position 0. So I'm going to place the element at the index, which is my count. And then I'm going to increase count by 1. I just have to be careful because at some point my array is full. And in that case, I shouldn't be pushing anymore, but I should kind of throw an exception. So that's what we do here. As long as there's still space, I can insert the element at the index, which is currently my count, and I have to increase the count by 1 because I added an element. Now pop, how do I pop? So first of all, I need to check whether I can actually pop an element, which means I have to check whether the stack is empty. So if it's empty, I shouldn't be popping. Otherwise, I'm going to take the element of not my current count, because that is unused, but just the position before that. That is an element that I'm going to that I want to return. So I need to store that, and then I can simply decrease the count by 1. So I don't explicitly need to remove the element from the stack. That will happen automatically. I mean, that will simply happen by decreasing the count by 1. In that way, I forgot about that element. So that's pop. Check whether there's actually an element that I can pop. Decrease the count by 1, and return that the element that is at that position then, so which was previously my count, but now -1. Okay, so we have implementations of all of these methods. What's the running time of these operations? So returning count, that takes constant time. Checking whether count is 0, constant time. Pushing is simply, moving count, storing an element, constant time. Popping likewise. So everything runs in constant time. The disadvantage now here is that in my example, I had a capacity of 20. If I want to store more than 20 elements, then I run into a problem. So what we would like to have is a stack where we can simply add elements, so push elements, and it simply grows if more space is needed. Now you might say, that's easy, we can simply use a Python list. If I append something to a Python list, then somehow that's always possible. And that's not a coincidence, because what we're going to look at here is actually the same, is essentially the implementation that runs in the background if you have a Python list. So what we want to do is we want to dynamically grow the array that we're using in the background. And we're going to look at two strategies for this. So the incremental strategy would be the following. So let's say I have a capacity of 20. Now I added 20 elements. Now I want to add the 21st element. So to do so, I simply increase the stack or my array by a constant size. So let's say again by 20. So then I'll have a capacity of 40. And okay, if I want to insert my 41st element, then I again add 20, and I always add 20. So that's called incremental strategy. In contrast, the alternative would be to say, when I run out of space, I simply always double the size. So let's say I start with 20, then okay, the next step would again be 40, because that's twice 20. But then if I want to insert my 41st element, I'm going to make my array size 80 and 160 and so on. So that's a doubling strategy. The problem here is obviously, I cannot simply resize an array. So an array has a fixed size. You should think of it as a kind of fixed chunk of memory. So what I need to do if I want to kind of move from 20 to 40 is I'm going to make a new array of size 40, and I'm going to copy all elements from the array of size 20 to my array of size 40, and then I can on position 21 insert my new element. So this is how this could look like in as Python code. So anytime, so this is simply the push that we've already seen, but anytime we run out of memory, so this would be the doubling strategy, we double the capacity, we make a new array, copy items it's called here, which has the new, as size, a new capacity. And then we have a loop which simply copies all the elements from the old array to the new array. And then we make the new array the array that we're going to store with our stack. It's that easy. But now, what's the running time of push? That depends on whether we need to construct a new array or not. So if we're simply, if we're not running out of capacity, it's simply the old push routine. It takes constant time. But now, if we need to make a new array and copy all elements, so copying one element takes constant time, but then copying all elements takes linear time in the number of elements. So one insertion in this case takes linear time, and that is true for the incremental strategy, but that is also true for the doubling strategy. So the worst case running time is linear for an insertion, which is somewhat unsatisfactory. It also does not allow us to distinguish which of these strategies would be better right now, incremental or doubling. So let's have a look at this in terms of the running time. So on the one hand, we see kind of an example where the incremental strategy, where we always add 5 elements. So in most cases, the running time is constant, but then every time we need to add capacity, we then get a running time, a linear running time. In contrast, in the doubling strategy, also in the doubling strategy we have the same, but we already see from these graphs that the doubling strategy seems better because this linear running time happens less frequently. And now we have to think about how do we analyze this. And the type of analysis that we're going to do is called amortized analysis. So we want to compare the incremental strategy and the doubling strategy. And looking at one push, so one insertion, doesn't really tell us much. So what we're going to do instead, we're going to look at n insertions. So T of n is now the running time of inserting or pushing n elements. And then the amortized time to push of the push operation, so the amortized time for pushing an element, is then T of n divided by n. So it's a kind of average. But I'm taking the average over what happens if I do n pushes and then divide that by n. And we're going to do the analysis of this. So how large is T of n for the incremental strategy and the doubling strategy? And then of course, how large is T of n divided by n in the next video. So what have we seen so far? We've seen abstract data types and data structures. And as an example, we've seen stacks and growable arrays. And next we want to see how to analyze growable arrays.